is a wealth of both current and future missions to track down and study planets orbiting distant stars known as exoplanets. But what does it take to launch an exoplanet observatory into space, and what can we learn from doing so? One such spacecraft is Cheops, a European Space Agency mission that has just begun collecting data. We spoke to the mission's project scientist Kate Isaak to find out more about Cheops' science objectives and what she hopes it might discover.
My name's Kate Isaak. I'm the Cheops project scientist. I work at ESA, which is ESA's technical heart in the Netherlands, ESA being the European Space Agency.
Thanks for joining me today, Kate.
Thank you for inviting me.
The reason that we're speaking is because of the Cheops mission, which launched in December 2019. And it's terribly exciting because it's starting to collect its first science and its first images and things like that. But I suppose it's worth just starting off talking a bit about the mission itself. First of all, what does the acronym actually stand for, and what will the Cheops mission actually do?
The acronym Cheops stands for Characterizing Exoplanet Satellite, and it's the first of ESA's exoplanet missions, which is dedicated to the study of exoplanets, so planets orbiting stars other than our own, planets outside our solar system. It's designed to search for transits of known planets that are orbiting bright stars using the technique of ultra-high-precision photometry. Now, it's a characterizing mission, as the name suggests, and by that I mean we will be doing a first-step characterization, a very basic characterization, whereby we measure very precisely the sizes of the planets, which we then can combine with the mass and volume gives us density, so the bulk density of the planet. This enables us to put constraints on the composition and internal structure of the planet, and with large samples of planets orbiting different types of stars at different orbital periods, we're able to study the formation and evolution of planets. This informs us on the evolution of exoplanets and, of course, of our own solar system. The mission's a collaboration with Switzerland, which leads a consortium of 10 other ESA member states, which all have key roles in the mission. It's a small satellite, as you may have seen, small both in terms of size, about 1.5 by 1.5 by 1.5 meters, and also, relatively speaking, for a space mission, it has a relatively small cost attached to it. This means that the who does what in the mission, so who is responsible for what, is a little bit different from typical ESA missions which you may be familiar with. So missions like Herschel, or missions that are coming up like Euclid, or even Rosetta, that you will have heard a lot about in previous Sky at Night interviews.
I suppose one of the questions that a lot of people would ask would be, there's so much being done now to study exoplanets, and it seems like there's kind of it almost seems like there's a new mission launched every month, although that's not actually the case. So how will Cheops actually stand out from the crowd? What is it actually going to bring to the exoplanet study?
The key thing about Cheops is it's a follow-up mission, and by this I mean that unlike missions like the CNES-ESA CORO mission or NASA's Kepler or TESS missions that were designed to search and find exoplanets, Cheops will follow up and focus on known exoplanets. So planet searches have revealed 2 previously unknown populations, so-called hot Jupiters, so puffy gassy planets orbiting very close to their host star, which makes them hot, puffy and gassy like Jupiter, as well as many smaller planets between sizes of Earth to Neptune, of which there are no analogues in our solar system. Now, it's more difficult to measure accurately the sizes of small planets, as one can imagine, because their signatures are generally smaller. And this is what Cheops will be able to do. It'll be very efficient at doing this, in fact, because if we know when and where to point, we know the host star that we'll be observing has an exoplanet, we can then catch the planets as they transit their host star. And we can keep coming back to build up the signal to noise on the planet and then to make the precise measurements that we need in order to be able to determine their size. We'll discover a few new planets in known planetary systems, that's clear, and that's very exciting, but it's not the main objective of Cheops. Something which will be very interesting is we'll be able to identify the smaller planets which have thin atmospheres, sort of like that of Earth, and so excellent candidates for follow-up with missions such as the James Webb Space Telescope and also future extremely large ground-based telescopes where we'll be able to characterise the atmospheres in detail. So much more detailed measurements than Cheops will be able to make, but Cheops is an important step in this process.
It's mind-blowing when you consider that we're actually able to create spacecraft that can do all this. So how actually does Cheops operate, and what sort of technique will it actually use in order to study exoplanets?
Absolutely, it is mind-blowing that we can observe, we can find the fingerprints or the imprints of planets outside our solar system. And to do this, we use the technique of high-precision transit photometry, and we infer the presence of a transiting exoplanet. So that's a planet moving across our direct line of sight of the telescope to the star, and this is what makes it transiting. So we're not actually measuring the signal from the planet itself, but a trace of it. In effect, a shadow that's created by the exoplanet. This is the same technique which has been used both on the ground and from space in other space missions to identify many of the more than 4,000 known exoplanets. What we do is to monitor the output of the host star before, during and after the transit, and to measure the light curve of the star. During the transit, the planet blocks a fraction of the light from the star. The amount depends on the relative sizes of the planet and the star, or more precisely, the areas of their disks. And the size of the dip is a measure of the ratio of this. So if we know the size of the star, we can get the size of the planet. Just to fix ideas, the size of the dip for Jupiter transiting the Sun, if we could observe this, would be about 1%. And for the Earth, it would be about 0.01%. So in order to measure precisely the sizes of planets, we need to be able to measure the precision, or to measure the light curves to a precision better than this. So this puts the limits on Cheops' performance requirements. So tens of parts per million on time scales of a few hours, the few hours being set by the duration of the transit, the few tens of parts per million set by the depth of the transit, because if you have a certain depth, you need to have the noise level at a fraction of the size of the depth. So we have high precision with Cheops and high cadence. And so with this, we'll be able to be collecting data points at a rate of 1 per minute. And we can use this to study not only exoplanets, but also stellar activity, so the host stars themselves, as well as solar system objects. Something interesting, hopping back to exoplanets, that we'll be able to do is to measure the light curves of stars over the full orbit of a number of exoplanets, the so-called phase curves. And with this, we'll be able to study the atmospheres and clouds on, for example, hot Jupiters, and see how they change over the orbital period of the exoplanet.
The spacecraft must be equipped with quite a lot of incredible science instruments in order to be able to carry out all these observations and send back the data. So, yeah, how exactly is the spacecraft equipped to do all this?
Cheops is very interesting. We actually have one single, perfectly formed instrument. It's an ultra-high precision photometer. The instrument is built around a single 1024 by 1024 pixel frame transfer CCD, which operates over the wavelength range of about 330 to 1100 nanometers. The CCD is sitting at the focal plane of a telescope which has an effective primary mirror diameter of about 30 centimeters. So this is small compared to ground-based telescopes, but it's perfectly suited for the purposes of Cheops. Now, what's key for us is the stability and the precision of the measurements that we can make. And the mission and the instrument have been designed with very high stability in mind. So to be insensitive to changes in temperature, for example. It's also very important to minimize the noise that comes into the instrument comes into the signal rather from the instrument and the environment. And so this is impacted on the design of our electronics and also the baffling of the telescope to keep out stray light from the Earth, as an example. And in this way, we're able to reach the precisions of tens of parts per million on the timescales of transits, which is what we need and what we're after.
Whereabouts will the spacecraft be located? Will it actually be orbiting Earth?
Absolutely. And you can actually see Cheops if you know where to look with a telescope. And this has been done. So Cheops is in an orbit at about 700 kilometers above the Earth. This orbit has a duration of around 100 minutes, and it's a little bit higher of an orbit than the Hubble Space Telescope, but significantly lower than, for example, a geostationary satellite. Now, the orbit is sun-synchronous and follows the so-called dawn-dusk terminator, which means it's possible to put the sun or to keep the sun permanently at the backside of the spacecraft. And this is very important to minimize stray light, which I mentioned as being a potential source of noise. We need to remove as much as possible noise from the Cheops measurements, and our orbit happens to enable us to do this. Not by chance, I should say.
How far away are the targets that it's actually going to be studying?
Well, Cheops targets are exoplanets orbiting bright stars, so typically F, G, K, and M dwarfs. And we focused on bright stars because these are those for which we'll be able to determine the masses of the planets using Doppler or radio velocity measurements, which you may be familiar with from the ground. And by bright, I mean stars which have V-band magnitudes up to 12, V-band magnitude of 12 or 13, maybe a little bit fainter, so out to a few hundred light years, depending on the spectral type of the star. So in the big scheme of things, relatively close by.
What sort of information do scientists back on Earth receive from the mission?
Well, first of all, they need to choose the targets to observe. And I think that's an important thing which maybe I can touch on, because the observing time on Cheops is split between the science team that's part of the Cheops consortium and also an ESA-run guest observers program. So the scientists at large can apply through a competitive process to observe with Cheops, which I think is a very exciting opportunity. Now, the science team has spent the last 5 years shaping their science programs and selecting their list of targets according to various science themes and topics which they've decided to focus on. These are improving the mass-radius relationship of exoplanets, starting to characterize the atmospheres of planets, looking in detail at transit light curves, and exploring and searching for new planets. There's, of course, the opportunity to do serendipitous observations of other sorts of targets, stellar physics, solar system objects. So I think there's the opportunity for many people to get involved with Cheops. The data that they will receive is quite broad. There'll be a number of so-called data products that scientists will be able to access, and these range from the raw images from the instrument itself to fully processed light curves that are produced by the data reduction pipeline that is used to correct and calibrate the data properly. We'll also have data from a wide range of sensors in the instrument and on the satellite, which can be used to do something called detrending, which is important in exoplanet science. And that enables scientists to remove time-varying signals that come from the satellite or from the instrument. Now, the data will be available from the Cheops mission archive, but it will be subject to a proprietary period, which gives the scientists that have spent a lot of time shaping the program of the mission and also putting in observing proposals to capitalize on their data, but then it'll be available for all to access through the archive.
The mission is actually already underway as we're speaking, and one of the things that really caught my eye over the past month or so was the initial images. And one of the things I was really intrigued to learn was that the first images that came back were blurry, but they were initially blurry. It wasn't like some sort of Hubble error, you know. Why were those initial images kind of purposely blurry?
That's a very interesting point. Yes, they were indeed purposely blurred. Perfectly blurred, I think, is how we like to refer to it. And this is a common technique which is used in exoplanet transit photometry. And what we do is to defocus the image in order to spread the signal from the star over a large number of pixels, or relatively large number of pixels on our CCD. And this makes us less sensitive to small changes in the direction in which the Cheops telescope is pointing. So we're stable to less susceptible to so-called jitter in the pointing of the satellite, and also less sensitive to small variations in the response of individual pixels on the CCD. So it's a well-established technique for getting very high precision photometry. The shape of the individual stars is an interesting one, as you allude to. It's triangular. The images are triangular in shape, and this is due to the way in which the mirror is supported. The primary mirror is supported, which puts its imprint onto the images of Cheops. But we can deal with that in the data processing.
Since its launch, what sort of data has it been collecting, and what has it been doing, really? Has it made any discoveries just yet?
Well, we're still in the very early days of the mission. Since in the period between early January and mid-March, we spent a very intensive period commissioning the satellite and the instrument. And by that I mean that the teams responsible for the spacecraft, the instrument, for the Mission Operations Center and the Science Operations Center, together with ESA, were working very hard to confirm that Cheops was working as we expected and as we need, and that it could be operated as required. And quite some time was also dedicated to determining how well the instrument was performing, how stable it was, and how accurately and precisely we're able to measure these light curves that I mentioned before, and from which we'll be able to get the transit depths and the sizes of planets. Now, during this period, we were able to observe a couple of very interesting transiting targets to exercise Cheops, shall we say. First was a transit of Kelt 11b, which is an 8-hour-long transit of a puffy gaseous planet, which is about 30% larger than Jupiter, and it's orbiting its host star in an orbit which is much closer to the host star than it is to Mercury. And the measurements that we were able to make were 5 times more accurate than those that were made from the ground, sort of illustrating the potential of Cheops. We also made some very interesting observations of 55 Cancri E, which is an exoplanet you may have heard of, a couple of times larger in size than Earth, again a short period planet, and we're looking to see what those observations reveal. Now, that was during commissioning, and from the 25th of March, the Cheops Consortium has been responsible for operating the telescope and the spacecraft from the Mission Operations Center at INTER near Madrid, with the Science Operations Center based in Geneva and the instrument team and instrument manager in Bern. So since mid-April, we've been working in so-called routine operations and observing targets that have been drawn from the pool of targets put together by the science team and through the guest observers program that I mentioned earlier. Now, a particular focus of the science team has been on a program to demonstrate the capabilities of Cheops, to showcase them, shall we say. And we expect to be publishing the first results from these in coming months. So I suggest you keep your eye out for this, for some interesting science.
Yeah, it sounds like it's going to be one of those missions that really does reveal quite a lot of surprises and a lot of discoveries. But for how long will it operate? And is there any chance of a mission extension, as kind of often happens with these missions? Yeah,
the nominal mission lifetime is 3.5 years. And we have a goal to operate for 5 years. And the clock started ticking on these timescales at the end of March. But we use very little fuel in our operations, and there are no other consumables for Cheops. So in principle, the lifetime of the mission is set by other factors. Now, the first one is, importantly, the funding, which is available to support operations. We have funding for 3.5 years, but we'll need to go back to ESA member states with a well-justified request for further funding. And the second is then performance. Now, Cheops is in an orbit above the Earth's the atmosphere, and this exposes it to radiation, which can damage the electronics of both the instrument and the spacecraft, and, of course, of the CCD. When I say damage, this is aging, which is expected and to a large extent understood. Now, there are ways we can compensate for this, for the effects of aging, but at some point this will impact on the performance that we get. Not for quite some time yet. So as to how long astronomers will be able to access the data will be available through the mission archive, and on the longer term it'll be put on into ESA's legacy archives, so it'll be available for a very long time to come. Scientists will have the opportunity to come back to the data, to come back to these very high precision light curves to see what's changed, what's the same, and what they can learn from future knowledge of these the exoplanets that will be studied.
I know we're only at the start of the mission, so this is probably quite premature, but are there any plans for future exoplanet missions at ESA, or are there any kind of exoplanet missions outside of ESA, for example, even that you're particularly looking forward to?
Yes, as you may know, a science mission takes a long time to develop from start to finish. In the case of Cheops, we first started working on the mission in around 2012, 2013, and we launched now. It's a small mission, so the timescale was reasonably short. So, of course, future missions are already under development. And Cheops is the first in a suite of 3 ESA exoplanet missions. The next one to fly will be Plato. So it's planetary transits and oscillations of stars. Again, it uses the transit photometry technique. And it's a survey mission, and it'll be dedicated to finding and studying large numbers of planetary systems with an emphasis on terrestrial-like planets that are in the habitable zone around solar-like stars. It'll also be able to study the seismic activity of stars to characterize the host stars and to determine their ages, which is an important parameter which is used to date the planetary system. The target launch date for Plato is 2026, so a little bit in the future. Then a little bit beyond that is then Ariel, which stands for Atmospheric Remote Sensing Infrared Exoplanet Large Survey. It's again using the transit technique, but this time using transit spectroscopy. So instead of using taking the broadband light to break that up into narrower bins, and to do transit spectroscopy in order to carry out a census of the atmospheres of around 1,000 exoplanets of different types and different temperatures. This will enable us to determine start to answer the questions of what planets are made of, how they form, and how they evolve. Now, this is in the late 2020s, both of these missions, or second half of the 2020s. On a much shorter timescale is the James Webb Space Telescope, which I mentioned earlier, and this will provide the opportunity to make some very detailed studies of the atmospheres of different types of exoplanets. It's an excellent opportunity for follow-up on some of Cheops's golden targets, and that is much closer in time to us than these 2 missions that I mentioned, Plato and Ariel. So it's a very exciting time for exoplanet scientists. We're building on TESS, which is flying now, of course, Cheops, which is really getting into its stride, shall we say. So I think it's a matter of watching this space and seeing how things progress. Very exciting.
Indeed, it really is exciting. It seems like we're on the cusp of real discovery, doesn't it? Thanks very much for speaking to me, Kate, and I just wanted to wish you and the rest of the Cheops team best of luck with the science, and we look forward to hearing all about your discoveries.
Very good. Thanks a lot for the opportunity to share what we know about Cheops and what Cheops will be doing. There will be more information available at links that I'll provide, and people are, of course, welcome to get in touch to find out more if they're interested.